So you may have noticed that our story for polynomials has sort of paralleled our story that we told for integers. For instance, we just finished talking about divisibility of polynomials. Back in the old days, we were talking about divisibility of integers. Well, we're going to continue this parallel track here by talking about the division algorithm for polynomials, which is, by the way, the division algorithm was exactly what came after divisibility when we were doing integers. So first, we're going to review what the statement and proof process was for the division algorithm for integers. Then we're going to see if we can figure out a strategy for the statement and the proof of the division algorithm for polynomials, and you'll be able to use those in working on the proof in the in-class activities. All right, so let's think about what the division algorithm for integers was like back in the old days. Right? So in the old days, we were dividing an integer b by some natural number a. And we, of course, wanted a quotient and a remainder. We needed to define what that is. We wanted that remainder to be non-negative. And we wanted the remainder to be small as possible. Small in quotes because that's a kind of a vaguely defined term. We'll get a little bit more precise on that a little later. So let's see what these three things mean or what they imply for what was going on with the division algorithm and for its proof. So first of all, what are quotients? What are remainders? And those turned out to be governed by an equation like this. B equals AQ plus R. Q was the quotient. R was the remainder. So remember, there are lots of different quotient-remainder pairs. If you don't have any requirements on what your remainder can be, whether it's positive, negative, how big it is, how small it is, you could have lots of different possibilities for both your quotient and your remainder. What does non-negative mean? Well, non-negative means that the remainder comes at or after 0 in the ordering of the integers. And this may seem an odd way of saying non-negative, but it does bring out this central issue that it requires our integers to be ordered. You have to have some kind of ordering to make non-negative make any sense. What does small mean? Well, small means as close to 0 as possible, as close to the beginning of the order. And that requires the integers to be ordered, and we needed the well-ordering principle to find the smallest possible one. So what's that going to look like for polynomials? Well, first of all, instead of dividing integers, we're going to be dividing polynomials. So we'll be dividing some g of x by some polynomial f of x. The equation for that, for quotients and remainders, is going to look exactly the same, except instead of having integers, we have polynomials. We have g of x equals q of x times f of x plus r of x. Q of x is the quotient, r of x is the remainder. Is it possible to have non-negative polynomials? That was one of the things that was really important. And as we noted before, that would require some kind of ordering on the polynomials, which we can't do. Polynomials don't have an order. So talking about non-negative polynomials, talking about smallest polynomials, right now is nonsense. But we're going to make it a little bit less nonsense by looking at some kind of stand-in for an ordering of the polynomials. So we're going to look for some quantity that measures sort of how big a polynomial is, and it has to measure it as an integer. And kind of the only tool we have available to us is the degree of a polynomial. Degrees of a polynomial, except for the zero polynomial, are integers, and so and they're not only that, but they're non-negative. They may serve our purpose as well. So using the degree of the polynomial as a stand-in for the ordering of the polynomials has some advantages. First of all, as I noted before, every polynomial has a degree, some kind of degree, except the zero polynomial. Remember that trying to define a degree on the zero polynomial causes some issues. The degree of any polynomial, if it has one, is non-negative, which is good, right? That's what we wanted for our remainders back in our integer days. And it suits our intuition pretty well. It's kind of easy to think of polynomials with higher exponents of x as being bigger than polynomials with lower exponents of x. Now there's a little disadvantage that we might have, and one is that we have lots of polynomials with the same degree. For instance, all linear polynomials, which there are a ton of them, have degree 1. And so what this means is that this is not a total ordering of the polynomials. It is only what we would call a partial ordering of the polynomials. And that also means that we might not have a unique ideal remainder. Remember, back in the old days, we were able to prove that both our quotient and our remainder are unique. We may not be able to do that with polynomials, but turns out we can get pretty close. So now let's start looking at the division algorithm proof, which seems really weird since we don't yet have a division algorithm theorem for polynomials. But that's okay. Let's look at the steps of our old proof and see if that can lead us to a good polynomial theorem and its proof. All right, so first of all, we want b equals aq plus r. That is what it means to have a quotient and a remainder. So what we did first was sort of construct the set of all positive non-negative remainders. And so we chose all whole numbers, x, that had the form b minus aq, where q is an integer. And of course, we got that by solving for r in the equation b equals aq plus r. Then we used the well-ordering principle to get the least element of s, right? And we called it r. And then we proved that that r is between 0 and a minus 1 with a proof by contradiction. And then we also proved that q and r are unique by, well, kind of by contradiction. It depends on how you look at it. At least the spirit of contradiction was in there. So now what are we going to do in the new days? Well, we want g of x equals f of x, q of x plus r of x. So we want to construct the set of all remainders. We want to choose the remainder r of x that is either the zero polynomial, that would be preferred, or has the smallest degree among all the remainders. Since our degrees are, one thing you might ask is why does such a polynomial exist? Well, it turns out the well-ordering principle is going to help us out because each of those degrees is a non-negative integer. And then you're going to be able to prove, of course, proving that r of x is less than f of x is a nonsense because we don't have any ordering on the polynomials. But you will be able to prove that the degree of r of x is less than the degree of f of x by contradiction, as long as r of x has the smallest degree among all remainders. And finally, you will be able to prove that q of x and r of x are unique by contradiction, as long as you put some extra requirements on r of x. Now, there are going to be parts of the proof that we're going to need to divide by some of the coefficients in order to make things work. So division really means you're multiplying by the multiplicative inverse, and we don't want to be hampered by the questions of, well, can we multiply by a multiplicative inverse? Does that multiplicative inverse exist? So that's going to require us to have all non-zero elements to have multiplicative inverses. Of course, we can't have 0 having a multiplicative inverse, so this is the best we can do. And that means that the ring of coefficients, right, the r and r of x, has to itself be a field. All right, so now I think I've set things up for you so that you can work on the in-class activities. The name of the file that you're looking for is Polynomial Division Algorithm.